Thank you for being here, and thank you, Nicola, for the introduction. So I will guide you to the steps that we took to develop an application on a hybrid system. We chose to develop on the NXP IMX7 processor, which has a Cortex-A7 core alongside a Cortex-M4 core in the same SoC. We have a master-slave architecture where the Cortex-A7 is the master core and the M4 is the slave. This means that the A7 is actually in charge of loading the firmware and actually release the Cortex-M4 from reset mode. So it takes, it is responsible for booting the M4. And from that point on, they run completely independently from each other, and they actually run at different speeds. So we need an interprocessor communication protocol to ensure that the two cores can communicate between each other. And the hardware module on the IMX7 board that it is enabling this kind of communication is the messaging unit, while the software component that enables communication is the rpmsg component, which uses the OpenAMP framework. We will see a little bit more in details of these components. The two cores in an asymmetric multiprocessing system actually access the same peripherals and memory areas. So we make sure that we have a mechanism to avoid conflicts. We will go into details of this. So the RDC is the resource domain controller, and it's a hardware module of the IMX7 processor that allows to create isolated resource domains. So basically, each peripheral or memory area can be assigned to one or more domain. Here in the picture, you can see we have the application core, which uses some this kind of peripherals exclusively, and then you can have, of course, shared peripherals. So the RDC makes sure that that access to shared resources is controlled and that there are no conflicts. This is actually the component that, the hardware component on the IMX7 processor that enables passing messages between the cores. So we basically have a set of registers and interrupts. We have two sets of matching register, one on each side. And we need two because the two processors can work at different clock speeds. So we need a way to synchronize them when they're passing messages between each other. Of course, you have interrupts to signal the other core when new data is available. And you have also 4 general purpose interrupts on each side that you can use for general purpose signaling. We actually used in our demo application some of these general purpose interrupts, and we will see later how. So as Nicola said before, the software component that enables communication, interprocessor communication, is rpmsg, and it sits on top of the VirtIO bus. So this is a quick overview of how VirtIO is implemented in the rpmsg framework. We have, in the VirtIO implementation, we have the VRing data structure, which has some VRing descriptors, which are basically pointers to shared buffers in memory, which represents our message, our actual message. And the VirtQ that we see here on the left is a user abstraction that provides access to this VRing structure and provides some APIs as well. So basically, our rpmsg component uses this VirtQ abstractions to send and receive messages in the form of buffers in shared memory. From the higher level view, we have the rpmsg component design here. Each remote core in the rpmsg framework is represented as a rpmsg device and provides a communication channel through the master core. So the rpmsg device is also known as rpmsg channel, and it has an ID, which is a textual name that is used to identify each rpmsg channel. It has a source address and a destination address. And on top of the rpmsg channel, we have logical endpoints that are provided by we have logical connections, on top of the rpmsg channels, which are provided by these endpoints that are represented here as these pipes. And each endpoint has a local address and a callback function associated to this address. So every time a new message arrives on the channel and has the destination address equal to the source address of the endpoint, the callback function is immediately called, and it can handle the payload of the message. One thing to keep in mind is that currently in the rpmsg implementation in Linux, the channel is only dynamically created. So the remote service sends a special message to the rpmsg bus, which says like, I want to instantiate a new channel. The rpmsg bus takes care of this message, creates the channel, and from that point on, an endpoint, a default endpoint is created, and communication can go on from this point. So this is the actual implementation of the rpmsg component on Linux. The remote core is, of course, represented as a platform device, which stands on the platform bus. We have this driver, which is the IMX rpmsg custom platform driver, which takes care of this remote platform device and registers a VirtIO device. Then we have another driver, which is the VirtIO rpmsg bus driver, which is like a bridge from the VirtIO bus to the rpmsg bus and registers an rpmsg device. Here we have one last custom driver, which is the rpmsg car driver, which is quite recent. It has been introduced in the 4.11 kernel Linux version. And of course, it registers itself as an rpmsg driver. And as soon as it is probed, it creates this character device here, which represents our remote core. So it basically exports the remote core abstraction as a character device, which is really useful if you have to write like a user space application and have to deal with communication with this remote core. So as soon as we have this device available, the user space application can do an IOCTL operation on this kind of device and ask for and request the creation of an endpoint. As soon as this happens, another character device is created, which represents the endpoint, and it's this dev rpmsgx character device. And from this point on, user space has access to the endpoint and can send and receive rpmsg messages just by writing and reading on the character device. So we developed a demo application on an IMX7 baseboard, which is the boundary devices Nitrogen 7. We are actually replicating the same demo on a carrier board by Toradex with the IMX7 SOM. And the goal of our demo was to have FreeRTOS running on the Cortex-M4 and Linux. I think the version was 4.9 on the Cortex-A7. So on the Cortex-M4 side, we are pulling an IMU, so an inertial measurement unit. We are reading data from the sensor, and we want to send them to the master core and visualize them somehow. One particular use case that we wanted to address was to safely recover from a kernel panic on the master core. We will see later all the details, but first I wanted to introduce you on how to build an environment or prepare your environment for developing an application on an AMP system. So the first thing you want to do is bring up your remote core, and of course you have to download the FreeRTOS sources, the GNU GCC toolchain, and you're pretty much ready to go, because in the FreeRTOS sources you have a subdirectory, which is examples, that has a bunch of applications already ready to be built for multiple boards. And you also have an ARM GCC subfolder where you have build scripts. So you basically can just launch those build scripts from shell and have your binary right away. Second step is to actually deploy the application on the Cortex-M4. You have a couple of choices. I usually prefer to do it from U-Boot. So I use the U-Boost Mass Storage gadget to mount the EMC on my PC, and I just drag and drop my binary. And then I use the M4 update U-Boot command to actually deploy the application on the Cortex-M4. You have a couple other choices. You can use also Remote Prop Framework, which is still part of the OpenAMP framework, and all documentation is under the OpenAMP documentation. Or you can use the M4 firmware loader from NXP. Either of these methods will do the job. It basically depends on when you want your Cortex-M4 to be started. Then you can choose from which memory you want to run your application from. The preferred memory is usually the TCM, so the tightly coupled memory, because it's a small, fast memory dedicated entirely to the Cortex-M4. The drawback is that it's only 32 kilobytes, so you have to make sure that your FreeRTOS application is optimized to fit into this small size. So as I said before, you can build your applications from shell very easily by using the build scripts. But you can choose, of course, to use an IDE. You have a couple of commercial choices. Here I reported DS5 or Sorcery Codebench, that they have like a lot of tools, especially tailored for EMP debugging. I decided actually to go with the plain Eclipse way, so I just took Eclipse and I equipped it with a few tools that can help debugging on AMT systems. I was using JLink Segger debugger, so I needed like this set of tools, which are the GNU MCU Eclipse plugins, to add support for my probe. Then, of course, you will need GDB. If you're using as well JLink debugger, you will need JLink scripts to debug both the Cortex-A7 core and the Cortex-M4 simultaneously. And then I use also the FreeRTOS kernel awareness plugin from NXP, which is not, it's the only thing that it's not open source, but it's really useful to debug FreeRTOS application. You can see like the status of your tasks, stack usage, heap usage, and everything that's useful for this kind of debugging. So after you set up your plain Eclipse IDE, it should look like this. You have, of course, the classic breakpoints view. Right now, I have only one breakpoint in the MCU, but of course, you can have multiple breakpoints on the MPU as well. You have your FreeRTOS kernel awareness plugin for debugging the tasks. And then, of course, you have consoles for debugging both the Cortex-M4 and the Cortex-A7 simultaneously. So back to our demo application that we developed. On the remote core, we have FreeRTOS application, and we sample the inertial measurement unit every 10 milliseconds. We calculate an objective function. In our case, was basically calculating the module of the vectors of the acceleration, accelerometer, magnetometer, and gyroscope data. Then we're storing these samples on a buffer, which is, in our case, is only 300 elements. And the reason that we use this queue, this size for our queue, is that we wanted to store our application on the TCM. So we only had like 32 kilobytes, so we have a pretty small buffer. But it's enough for the demo we are studying. And then items are dequeued from this buffer and sent to the master core for visualization. So we sent 10 items at a time and every 100 milliseconds. On the master core, we have a much simpler application. It's a user space Linux application that just pulls the character device, which represents the rpmsg endpoint, and dumps the data received on a text file. So here we have an overview of the architecture of the demo application. And on the left side, on the right side, sorry, we have the Cortex-M4, which is running FreeRTOS. And we have two asynchronous tasks. We have the emu polling task, which actually continuously polls the emu and enqueues our samples in the share buffer. And then we have the data sender task, which is in charge for the initialization of the rpmsg channel, and it is in charge of dequeuing samples from the shared queue and sending it to the master core. Here we can see the rpmsg channel as well as the endpoints. And on the left side, we have the Linux side, so our master core, which is running Linux. We can see the rpmsg car kernel driver, which exports our endpoint data as character devices. And finally, we have our user space application that interacts with the character devices to read data and dump data on a text file. We also used 3 general purpose interrupts that were provided by the messaging unit to actually signal some states of the master to the remote core. These are all triggered by the master towards the remote core. We call them start CMD, stop CMD, and heartbeat. So start CMD is an interrupt that it's used to signal that the master has created the endpoint and it's ready to receive data. Stop CMD is used to signal that the endpoint has been destroyed, and this actually happens every time we close the rpmsg card client applications, since there's no need of keep receiving data if we're not using it. And the last one is the heartbeat. So we needed a way for the Cortex-M4 to know whether the Cortex-A7 was still up and running or if it crashed for some reason. So basically we're generating an interrupt from the master periodically, and the Cortex-M4 just checks if these interrupts arrive at certain times, and if it doesn't, it just assumes that the master is dead for some reason. So yes, this was the previous image, and you can see we have the same, pretty much the same structure. Here we have the control flow on the 2 cores. So on the left side, we have rpmsg card client on the Linux, so the Linux user space application. We have a first transition from a state where the rpmsg channel is not created to a state where it's up. Then the user application just opens the dev rpmsg0 character device, and with this action, the endpoint is actually created. And then we stay in this S2 state. We just keep reading data incoming to the rpmsg channel. And then when we want to close our application, we just close the dev rpmsg0 character device. The endpoint is destroyed, and that's it. On the right side, we have the flow of the data sender task on the FreeRTOS side. Also here, we have a first transition from where the channel is not there to the state where the channel is created. Then we just, our task just waits for start CMD interrupt, goes into this state where it just keeps sending the EMU samples to the master core and checks for the master heartbeat. If stop CMD interrupt arrives, it just goes back to just reading samples from the EMU and buffering data. And if the master heartbeat doesn't arrive on the expected time, the MCU just assumes that the MPU has crashed and goes back, destroys the channel, and goes back to first state. So we had to figure out what to do if the Linux kernel panic on the master side. Using a watchdog to just trigger a full reboot was not an option here, because in the IMX7 architecture, if you reboot your Cortex-A7 core, also the M4 core will be rebooted. We still wanted the application to keep running on the Cortex-M4 and just reboot the Linux kernel on the A7. So the solution we came up with was to use kexec, which allows to load kernel from the currently running kernel. And the reason we chose kexec is that it does not reset all the hardware devices, but it's just like a soft reboot. And so it doesn't actually touch our application running on the Cortex-M4. This mechanism is usually used in conjunction with kdump to also dump the crushed kernel memory for further debugging. We actually didn't use kdump in this demo application. We only needed kexec. We also used two kernel images, one that it is booted every time normally in a normal boot, and one that it is executed only in case of a kernel panic. So we had to add some extra options, both to the normal kernel command line and to the crash kernel command line. And then we had to use like this option to signal that the crash kernel has to be loaded only in case of a kernel panic occur. Keep in mind that kexec and kdump support on our platform is still experimental, so we had some problems with the demo. We solved some problems, and we still have some other ones that we need to have a more detailed look at. But we will see what are the problems that are still open in our demo. So we have a video of the demo. So let's see here. So what we have is, on the left side, we have the Cortex-A7, which is booted in Linux. And on the right side, we have our Cortex-M4 with FreeRTOS. You can also see that the FreeRTOS application has already started and has initialized the sensors. And it's actually already sampling the EMU and buffering our data. So as soon as the Cortex-A7 is up, we just log in. And we launch our rpmsg car client application, which is the user space application. And we can see that the data is starting to flow from the Cortex-M4 to the Cortex-A7. Yeah, we are writing our samples in a text file. You can see that data is correctly arriving on the master side. Then here we are loading the crash kernel with the options that we saw earlier. And here we are actually causing a kernel panic. So here you can see that the Cortex-M4 said master is dead, so it actually realizes that the master core is not up anymore, and it just keeps running. And the Cortex-A7 is rebooting its crash kernel. So as soon as the crash kernel is up and running, the rpmsg channel is recreated again. And we can relaunch our user space application to see that data is still recovered. That's what we're doing here. So Cortex-M4 starts sending all the data that it has sampled and buffered to the Cortex-A7, and data is still arriving on the master side. So that's it. Back to our presentation. Any questions? Yep.